Welcome to our deep dive into the core concepts of deep machine learning. This video is for anyone looking to understand the fundamentals of this powerful technology. We'll start with a brief introduction to set the stage for what deep learning truly is. Deep learning is a subset of machine learning that uses neural networks with multiple layers, enabling systems to learn from vast amounts of data. Throughout this lecture, we'll cover essential topics including neural networks, activation functions, loss functions, gradient descent, and the chain rule. Let's begin with the foundational element of deep learning, the neural network. At the heart of every neural network is a single neuron. But don't let the simple name fool you. Inside this digital cell, a precise four-step calculation is happening at lightning speed. Let's go under the hood. First, the neuron receives data. These are the inputs. But not all data is created equal. Each input is multiplied by a weight. Think of the weight as a volume knob. A high weight turns the signal up because it's important. A low weight turns it down. Technically, we're calculating X times W for every incoming signal. Next, we add the bias. If the weights are the volume knobs, the bias is the master on/off threshold. It represents how easy or how hard it is for this specific neuron to fire, regardless of the data it's getting. Now the neuron bundles it all together. This is the summation. It takes all those weighted inputs, adds the bias, and collapses them into one single number. This number represents the total evidence the neuron has gathered. Finally, we reach the gatekeeper, the activation function. This is a mathematical filter, like ReLU or Sigmoid, that decides the final output. It asks, is this total signal strong enough to pass forward? If the answer is yes, the neuron fires, sending a signal to the next layer. If not, the signal dies here. Input, weight, bias, and activation. This tiny cycle repeats millions of times across a network, turning raw numbers into intelligence. A basic neural network is built from layers of these neurons, taking inputs, applying weights, and generating an output. Next, let's explore activation functions, a critical component within each neuron. The primary purpose of an activation function is to introduce nonlinearity, allowing the network to learn complex patterns and make decisions. Common activation functions include ReLU, Sigmoid, and time, each with specific use cases and advantages in network training. Imagine a neural network trying to identify a cat in a photo. Thousands of neurons are firing, but not all of them are seeing anything useful. That's where ReLU comes in. It's the gatekeeper that separates the signal from the noise. A single neuron in the ear detection layer calculates its weighted sum. It looks at a patch of pixels. If it sees a sharp triangular shape, its internal number, the weighted sum, shoots up to, say, +10. It found a cat ear. Now, ReLU steps in. Its rule is simple. f of x equals max, 0x. Because 10 is greater than 0, ReLU lets that 10 pass right through. The neuron fires, telling the next layer, hey, I found an ear here. But what if the neuron is looking at a flat, blurry background? Its calculation comes out to a -5. This is noise. Without ReLU, that negative signal would clutter the network. But ReLU sees the -5 and instantly turns it into a 0. Technically, we call this sparsity. By zeroing out everything that isn't a cat ear, ReLU shuts down irrelevant neurons. This makes the AI incredibly fast and efficient. It doesn't waste energy on maybe. It only cares about yes. Simple, linear, and lightning fast. That's ReLU. The reason modern AI can process millions of images in the blink of an eye. If ReLU is a light switch, either on or off, then Sigmoid is a dimmer. It doesn't just say yes or no, it tells us exactly how confident it is. Let's see how it decides if that new email in your inbox is actually spam. The final neuron in the network has gathered all the evidence. It's seen words like free, winner, and urgent. Its internal calculation, the weighted sum, is a high number, maybe a +4.5. But what does that number actually mean for a human? This is where the Sigmoid function works its magic. It takes that +4.5 and crushes it onto a curve between 0 and 1. Mathematically, it uses an S-shaped curve, the Sigmoid curve, to transform raw scores into a percentage. The result? That +4.5 becomes 0.98. In human terms, the AI is 98% certain this email is spam. If the score was a negative number, the Sigmoid would drop towards 0, signaling a, quote, safe email. It gives us a nuance that a simple on/off switch can't provide. This is why Sigmoid is the king of the output layer. It turns abstract math into a probability we can actually use to make a decision. It's the difference between a guess and a calculated risk. ReLU finds the features, but Sigmoid makes the choice. One is for speed, the other is for certainty. Dense layers connect every neuron in one layer to every neuron in the next, providing the core structure for complex feature learning. If the first layers of an AI are the eyes that see shapes, the dense layer is the brain that understands them. This is where the network stops looking at parts and starts looking at the whole. Technically, it's called fully connected. That means every neuron from the previous layer has a direct line of communication to every neuron here. No detail is left out. It takes all the scattered clues found earlier and weaves them together. This is where the weighting really matters. The dense layer learns that a, quote, triangular ear plus a whisker equals a cat. It's the layer of global reasoning, filtering out the background noise and focusing only on the features that lead to the final answer. T is the final funnel. It takes thousands of complex signals and narrows them down to a single, confident conclusion. Without the dense layer, the AI would see the trees, but never the forest. A neural network learns by making mistakes. But how does it know how to fix them? The answer lies in the power of the derivative. Imagine the network predicts a dog when the image was actually a cat. The loss function measures that error. Now the network needs to backtrack. It asks, which specific weight in my millions of connections caused this mistake? The derivative acts as a compass. It calculates the slope of the error. If the slope is steep, the network knows it needs to make a big adjustment to that weight. If the slope is flat, it knows it's getting close to the truth. Using the chain rule, these derivatives flow backward through the layers, a process called backpropagation. It's a global performance review, updating every single neuron so that next time, the error is smaller. Without derivatives, AI would be a static set of random numbers. With them, it becomes a system that can learn, evolve, and eventually reach near-perfect accuracy. By using these derivatives, we can effectively adjust the network's weights to minimize the loss and improve performance. Now let's talk about how we quantify the error in our predictions using loss functions. The loss function, or cost function, is crucial as it measures how well the model is performing by quantifying the difference between the model's prediction and the actual value. With the loss function defined, we optimize our network using gradient descent. The chain rule is fundamentally important in backpropagation, allowing us to efficiently calculate the gradients for every weight in the network. There are three main types of gradient descent: batch, stochastic, and mini-batch, differing in how much data they use for each weight update. Each type of gradient descent involves trade-offs. Batch is stable but slow, stochastic is fast but noisy, and mini-batch often strikes the best balance. While artificial neural networks, or ANNs, are general purpose, convolutional neural networks, or CNNs, are specifically designed for processing grid-like data, making them ideal for image recognition. We have covered a lot of ground today. Let's briefly summarize the key concepts. We explored neural networks, activation functions for nonlinearity, loss functions for error measurement, and gradient descent for optimization using the chain rule. We hope this foundation helps you as you continue your journey in deep machine learning. Keep practicing and explore more advanced topics next. We will cover each topic and deep dive in next videos.